As you all know, epidemiologists and biostatisticians work very closely together. So we need to have some understanding of each other's discipline. So this is the first of three short talks on random error, three aspects of random error, and it's the closest we come in this course to talking about statistics. I've done my best to make it as intuitive as possible and not really go into the calculations at all, but to give you some understanding of things like hypothesis testing, power calculations, confidence intervals and p-values and so on. So let's start by talking about validity and precision. But just to say that there's a word, accuracy, which sums up validity and precision. We try in our epidemiology studies to produce results that are as accurate as possible, and accurate in terms of representing the measure in the broader population. And accuracy is really has two components: validity and precision. So when we talked about bias and confounding, we were really referring to validity. And now that we're talking about random error, we're going to be talking about precision of results. And these are the two most important considerations in the design, conduct and analysis of really any epidemiology study. So basically we say that validity is determined by the absence of systematic error or bias of effect estimates, and precision, which is really a measure of repeatability, if we're able to carry out the study multiple times in the same population, how closely the results that we got from these multiple studies would resemble each other. And this is really largely determined by the elimination of random error, and we can refer to that random error as non-systematic error. So this is a diagram which attempts to sum up random error and systematic error together. So you can see we have a true value. So we're looking at a relative risk, so it could be a risk difference or an attributable fraction, but we'll stick with relative risks. And there is some truth out there. We may not know it for sure, but we design our study to try and get it, try and make our estimate of the relative risk as close to the truth as we possibly can. But we may have some bias in our study design, or the way we collect the data perhaps, or the way we recruit participants. And so that bias is represented by this difference here between the value of the relative risk we actually obtained in our study and the truth. So we don't actually know what that difference is, but we try and minimize the difference by minimizing sources of bias in our study. But the other sort of error that we have to contend with is random error. So you can see that the value that we obtain from the study has this bell-shaped curve around it, and we're going to talk about that in a bit more detail. But basically, this represents the distribution of possible results we might get given a certain sample size, and given that there's going to be some random variation in the data. And so they will be somehow centered around this line, which is this median line, which is determined by the degree of bias in our study design. But there's going to be some wobble, and it's going to be a function of our sample size. So we'll describe that in more detail. So that's how you can think of systematic error and random error in one picture, if you like. So we can think of any epidemiology study as involving a sample of some larger population, and basically the idea of taking a sample is to estimate the size of some measure, which could be a prevalence or relative risk or risk difference or incidence or whatever, in the larger population that we're sampling from, because we just can't afford to collect data from the entire population, so we take this sample. Now, there's always going to be some random variation from sample to sample, and we can say that as a general rule, smaller samples have less precision. They have more sampling variability, much more wobble in the results. But as we increase our study sample size, then the degree of random error will decrease, but the bias will not. So you can think of it in this way. So this is the amount of error, but the systematic error or the bias is basically inherent in our study design, where we've recruited participants and so on. So it stays pretty fixed. But random error, we can do something about that. We can increase our study sample size, and then random error will drop off in some way. So again, that's another way you can conceptualize systematic error and random error in one single diagram. Now I want to move to talk about hypothesis testing. First of all, in the broadest sense, right across science, we usually start by generating hypotheses, and these may be entirely intuitive, maybe from observing the world and coming up with some ideas about causal relations in the world, and that X causes Y or whatever, and then we design an experiment to test them, to test our hypothesis. And in some disciplines, and we'll talk more about this in a future talk, the idea is to falsify our hypotheses. We try and falsify our hypotheses, and we'll come back to that concept. But basically, practically, in epidemiology, very often we carry out our hypothesis testing by comparing our observed distribution of data. So our observed distribution of data is what we obtain from our study. And then we compare it with what we think is the expected distribution under the hypothesis. And then we compare the two hypotheses, the two distributions statistically, and see whether there is there's evidence that there's a real difference using statistical tests. And so what we're interested in is whether if there is a difference between the two distributions, whether it could be explained by chance or not, or whether it seems to be beyond the bounds of reasonable chance. So very often in epidemiology, we compare our what we might call our alternative hypothesis with the null hypothesis. So usually we're comparing our ideas against the null hypothesis. So the null hypothesis is basically that nothing is going on. So it could be a relative risk the same is equal to 1, an odds ratio equal 1, or a risk difference equals 0. Anyway, we'll have some null hypothesis suggesting there's no association between an exposure and a health outcome. And so most of the testing we do, the statistical testing we do, make the basic assumption that the null hypothesis is true, rather than some alternative hypothesis. And we test the alternative hypothesis, HA, against H0. And we apply a statistical test. And very often the statistical test gives us a p-value. So what's a p-value? And so a p-value is not the probability that the two distributions are different. It's the probability that the observed result, in other words the result which we get from our study, or a result more extreme, or further from the null. So in other words, what I mean by that is if we observe an odds ratio, say, of 2, anything more than 2 would be regarded as more extreme, in other words, further from the null. And the question is, what's the likelihood, the probability of getting that by chance alone, if the null hypothesis is true? So this is very important, if the null hypothesis is true. So another way of thinking about this, it's the likelihood of obtaining a false positive result in our study, simply due to random variation in the data, if the null hypothesis is true. And that's a very important caveat that always needs to be added. And so the p-values, they can range from 0 to 1, and they assume the absence of bias, including confounding. And we're going to come back to that, and why that's very important. A lot of people overlook that. They think of p-values on their own. They forget that p-values may be severely affected by bias in our study. Okay, so small p-values, which indicate the probability that a low probability that the observed result would have occurred by chance alone if the null hypothesis was true, suggests that the alternative hypothesis is perhaps more likely to be true. And or another way of putting it is we can say that the that a very low p-value suggests that study data are not consistent with the null hypothesis, because the likelihood of them occurring by chance that result occurring by chance is pretty low, and that a small p-value suggests that the alternative hypothesis would be a better explanation for the data rather than the null hypothesis. But because it's a matter of probability, we cannot say that it's impossible. The chances are an impossible explanation. You say it's an unlikely explanation, because even very extreme results are possible just by chance alone. Okay, so back in the early part of the 20th century, a number of statisticians decided that, quite arbitrarily, that a p-value of 0.05, in other words 1 in 20 or less, would be designated as statistically significant. So what that means really is a false positive rate of 1 in 20 would be regarded as statistically significant, because they considered that that was unlikely to occur by chance. But of course it can occur by chance. But they acknowledged that, and they decided this was an acceptable false positive rate if the null hypothesis was really true. So it's not always the case that we would say that this is an acceptable false positive rate. It depends on the seriousness, really, of actually having a false positive. In certain circumstances, it could be a very serious result if it was a false positive. So, but nonetheless, it's kind of come down through the decades as kind of denoting statistically significant. And it's often, this value of 0.05 is often designated as alpha, and we'll come back to alpha. Alpha is not always 0.05, it may be something small like 0.01, but it is whatever the measure is that's regarded for the purpose of the particular experimental study as being the cutoff point for statistically significant. So say we get a p of less than or equal to 0.05. If we follow the kind of the traditional way of doing things, we might say the results are unlikely to be due to chance, and then we might reject the null hypothesis, or another way of putting it is do not accept, which is really sort of hedging our bets a bit more. Do not accept rather than reject the null hypothesis in favour of the alternative hypothesis. On the other hand, if the p-value is greater than 0.05, we might say that the result that we obtained in our study is likely to be is quite plausible, quite probable that it would be caused by chance, a result alone, and we do not reject the null hypothesis, or we might say we accept the null hypothesis. Those different phrasings basically meaning the same thing, and some people prefer one or the other. Now, the thing about statistical significance testing, it's really a decision-making criterion, and that and it was really, in the original days, it was applied along those lines, because a lot of the original statistical work for which these tests were developed came out of sort of agricultural testing different ways of treating plants to see which methods kind of cause them to grow better, how much water and how much fertilizer and all that sort of thing. And so they use this as a decision-making criterion to sort of move through various steps in their experiments. But nonetheless, it's been kind of handed down to other disciplines such as epidemiology, and we inherited the statistical significance testing. But we'll talk about it's not so much used anymore for reasons I'll describe. Okay, so we carry out an epidemiology study, and we end up basically with with several situations. So we have our study result, and then there is the truth, which we don't necessarily know. So for the truth, which is not usually revealed to us, there are two possibilities. it could be that there's really no association between the exposure and the health outcome. So in other words, the null hypothesis might be true, or it could be that in fact there is some association. So those are the two possibilities. So we've got a study result, and based on the p-value from the study result, it might tell us we should accept the null hypothesis or reject the null hypothesis. So basically there are four possibilities that can then occur, and two of them are correct. One of them is that the correct decision is made. We accept the null hypothesis, and it's actually the truth is that the null hypothesis is actually true. So that would be a correct decision. It's a true negative. Now the other true decision is that the null hypothesis is not correct. The alternative hypothesis is correct, and we actually, on the basis of our study result, we decided to reject the null hypothesis. So these two are correct decisions. That's a true positive and the true negative here. But then we have the other two situations where in actual fact, the null hypothesis is true, but we decide on the basis of our study result to reject it. And that would give us a false positive, which we sometimes refer to as alpha. Alpha again. And then the other one is the truth is that the alternative hypothesis is true, but because of our study result, which seems to indicate that the null hypothesis is true, we accept the null hypothesis. So that would be a false negative, sometimes designated as beta. I'm going to come back to alpha and beta. And also the correct decision, true negative, we would sometimes designate 1 minus alpha, and the true positive we sometimes designate as 1 minus beta. And this will turn up again in a minute in my next talk, in fact, as statistical power. This represents statistical power. Okay. So the limitations of significance testing using this arbitrary cutoff point of p less than or equal to 0.05. So first of all, you can have a huge sample from a population if you have a big budget, or have some way to collect a lot of data from a lot of people, and so that you may have a very trivial, say, relative risk increase, might be sort of 1.1 or even smaller, but the sample size is so huge that the increase, or it could be a decrease, it could be less than say 1. But it comes out as statistically significant according to our test. So, but in actual reality, the difference is in practice relatively trivial between the groups being compared. On the other hand, if you have a small study sample, and you may not even be able to detect quite a large risk increase or a risk decrease for that matter, because it won't be designated as statistically significant. So that's a problem, because the p-value actually gives you no indication of the sample size, and so very often, unfortunately, people focus on whether or not something was statistically significant or not, but it may be irrelevant just because of your sample size. So that's a problem. And then if you have a situation, if you use this kind of decision-making criterion of 0.05, if you have two results, 0.04, a p-value of 0.04, or a p-value of 0.06, then if you apply that decision-making criterion rigidly, then you would come up with a completely different decision. Here you might reject the null value, the null hypothesis, and here you might accept the null hypothesis. But really, it just a bit of random variation could easily switch the p-value from 0.04 to 0.06. It's easily done with just a sort of few people, sort of, few more people getting the disease, or a few less people getting the disease, say, and then the p-value can change quite, from one side of the 0.05 cut point to another. So really, it's a very arbitrary thing. It's very well, just arbitrary. It's not very useful. And let me just illustrate the problems of sample size. So here we have a coin which is possibly biased. We wonder if it's biased, and we would expect if we flipped a coin 10 times, then we would get our expected value will be 5 heads and 5 tails. On the other hand, say we carry out an experiment and we get 7 heads and we get 3 tails. So the odds of getting 7 heads and 3 tails, it's 2.33, and 2 extra heads over the number of tails, and we can calculate a p-value for this, 0.65. And so we would say, well, there's really nothing much in this. The excess of heads to tails could easily be due to chance, so that's true. On the other hand, we take the same coin and we flip it 100 times rather than just 10 times, and we would expect 50 heads, 50 tails, but if we end up with 70 heads and 30 tails, the same odds, 2.33, but this time we have a bigger difference, of course, and if we carry out the same statistical test, we'll get a p-value of 0.006. So in this situation, we'd say the excess of heads to tails is very unlikely to have occurred by chance. And yet it's the same coin, simply the sample size is different. In one case we were using 10 tosses of the coin, in the second case we're using 100 tosses of the coin, and we get a completely different result. One statistically significant, the other not. And so it's a simple way of illustrating the importance of sample size. So, for the most part in epidemiology these days, we try and avoid statistical significance testing. It's simply not necessarily in the majority of situations in epidemiology to make some sort of firm decision, because the p-value, the cut point of 0.05 is really a decision-making criterion. But why should we be forced to make decisions on the basis of one study, one statistical test? So we are much more inclined to kind of compile information from a lot of sources and a lot of different studies. We're going to be talking about that in a lot more detail in a future talk. But unfortunately, sometimes we need to make decisions, and a couple of those situations are here, are mentioned here. One of them is the test of heterogeneity of results when deciding whether results can be combined. So we talked about, when we talked about confounding, making some decisions about whether or not to combine data from strata, different strata, when we to calculate a Mantel-Heinzel odds ratio, say. And though we can often eyeball the results to see whether the stratum-specific odds ratios or relative risks look similar, sometimes we are not sure. And there are tests of heterogeneity that can be carried out. And these tests produce a p-value, and usually we use the p-value to make a decision as to whether or not we can combine the strata. So the p-value, if it's low, we would reject the null hypothesis that being that the odds ratios for the different strata are the same. If we have a low p-value, we would decide that we cannot combine them. If we have a high p-value, we decide that there's no evidence of heterogeneity, and so it's okay to combine the strata, calculate a Mantel-Heinzel odds ratio. So that's the situation, one situation where we would potentially use this decision-making criterion. And the second one is when deciding the adequacy of our sample size for a particular study. And in my next talk I'm going to be talking about sample size and statistical power, the two things which go hand in hand in any epidemiology study. So just finally, just to finish this talk on hypothesis testing, as I said, people, well, in the older literature in particular, you often used to see people just sort of indicating whether a result was statistically significant or not, and so there will be like 1 asterisk or 2 asterisks depending on the cut point, whether it's 0.05 or 0.01, but the actual p-values were not actually mentioned. Now in epidemiology, insofar as we use p-values, we usually present the actual value itself, because that's far more informative. And you can see, for example, these couple of examples here, we could, as it was things used to be presented, use just a p-value of less than 0.05, but we might have two underlying p-values of 0.04 or 0.001. Really, they have very different meanings in terms of the likelihoods of these results occurring by chance. So there's no point in kind of representing them both by the same rather uninformative indicator, which is the p of less than 0.05. Similarly, we might have a p of, we might represent our results with the p of greater than 0.05, or we might just not have any p-value at all, which is often the case in the older literature. But it's much more useful if we actually present the actual p-values, such as 0.06 or 0.72, both of which are represented by this, by greater than 0.05. So, I mean, the basic point here is avoid these statistical significance indicators, and in your publications, present the actual p-values, because 0.72 and 0.06 are really quite different indicators of the likelihood of something occurring by chance. So that's all I want to say about p-values for the moment, and statistical significance testing. In the next talk, I'm going to be talking about the concept of statistical power and the things that influence it.